In the next section, we are going to deal with complete problems. This means something theoretical now. As I mentioned in the very first video, the optimistic attitude of the 50s and 60s had been ruined in the 70s by the theory of NP completeness by Cook and Karp. So they proved that there existed, or rather there probably existed, algorithmically intractable problems. Therefore, the main goal of the next section is to get acquainted with the NP completeness. Although, as we all know, NP is not the only complexity class in the world. Obviously, the concept of completeness can be extended to all the other complexity classes. Thus, there exist P-complete, X-time complete, P-space complete problems too. But first, let's slow down a little bit. I am trying to explain first what it means for a computational problem, let's call it a language, to be NP complete. On the one hand, it has to be shown that this language L belongs to NP. In the previous section, we have got acquainted with a powerful and relatively easy to use tool. This was the witness theorem. By applying this tool, we are able to show relatively easy that L belongs to the complexity class NP. Here the question is if the same language L belongs to the complexity class P as well. If it does, then L is tractable for deterministic Turing machines, that is for today's computers. Consequently, we do not really need non-deterministic Turing machines to solve L. To sum up, given a language L in NP, is it possible that L belongs to P as well? So this is the question. The concept of NP completeness was invented to make easier to deal with this question. NP completeness means something like this. Given a language L, which we showed to belong to NP, if L is NP complete, then all the languages in NP can be reduced to this single language L. Reducibility means that all the words of another language can be translated to the words of L. For example, the words of a graph problem, for example, graphs, can be translated to the words of a numerical problem, that is to numbers. This is like we employ a translator guy who can translate the words of a language to the words of another language. Why is it beneficial to have such a translator? Because we know that the language L can be decided in a polynomial time by a non-deterministic Turing machine. Now, this very same Turing machine can be used to decide all the NP languages. We only need to translate the words of all those languages to L, and then we can apply the algorithm, the Turing machine, which decides L. I hope everything is crystal clear. Okay, to sum up, by showing that the language L is NP complete, we make the algorithm that decides L a universal algorithm that decides the entire NP class. This is a very powerful feature. The question is if there exists any complete language at all. Well, no matter how improbable it seems, there exist such languages, several ones actually. The other question is if those NP complete languages are also in P. If they were, then all the NP languages could be solved by the algorithm that decides this NP language. That is, all the NP languages could be decided in polynomial time by a deterministic Turing machine. In other words, all the non-deterministically tractable problems would also be deterministically tractable. Thus, all problems being tractable by quantum computers are tractable by today's computers too. This is the main question. No matter how strange it is, no one has been able to answer this question so far. No one. No one has ever proved either that P and Ampli are equal or that those two complexity classes are not equal. So now let's analyze the two possible answers. What would it mean if the two complexity classes were equal? Then, as I've just said, all the MP problems could be solved by deterministic machines. And then what? Well, as I've also told it before, today's computers could probably break all the cryptographic protocols. Okay, so what would it mean if the other choice held, that is, P was not equal to NP? Then we could stay calm, since the MP problems couldn't surely be solved by deterministic machines, that is, by today's computers. Thus, the cryptographic protocols wouldn't be in danger, while, of course, people use deterministic machines.